Hi, this is Inhwan Bae. In this video, I'm introducing a groundbreaking language-based method for predicting trajectories. The goal of predicting human trajectories is to infer socially acceptable paths based on previous movements. These crucial tasks support a variety of applications, including self-driving cars, delivery bots, urban planning, robot navigation, and surveillance systems. To predict future paths, the model first analyzes the coordinates of all pedestrians in a scene. By observing the past 8 frames and checking interactions among pedestrians, the model forecasts the trajectories for the next 12 frames. Here, the trajectories consist of sequence of coordinates, with the coordinates being numerical values on the xy plane. Due to these characteristics of the data, trajectory forecasting can be considered a form of numerical regression, which predicts the most likely coordinates based on training data. Leveraging the numerical nature of these coordinates, trajectories have been generated through physical modeling, generative modeling, and diffusion-based modeling. The models are trained using a loss function that minimizes the numerical distance to the ground truth. Additionally, under this predictive pipeline, feature distance-based social relationship modeling have been conducted. Although the numerical models have become increasingly complex in order to more effectively mining meaningful information from these numerical data, they are still limited to using only numerical data. Meanwhile, language models have made rapid advancement recently. These recent advances have showcased their capability to understand context and perform conditional generation across a wide range of tasks. These advances mimic human thought processes. In real life, as people navigate streets, they plan their routes guided by language-based thinking. For instance, when facing with an intersection situation, a person might think, once the car passes, I should turn left toward the entrance for safety. This thinking guides their interaction with their surroundings and help them plan a safe path. Inspired by this, beyond the traditional numerical-based approaches, we design a language-based modeling that performs human-like thinking. To achieve this, we present a trajectory prediction framework based on sentence generation called RM trajectory. Our framework begins with multimodal inputs that include trajectory coordinate data and scene images. To mimic human thought, all input modalities are converted into natural language. We then introduce a question-answering template. This method provides the language model with the trajectory coordinates and environmental information as context and trains it to respond to the questions. Consequently, the language model perceives human dynamics as a type of language pattern and makes its final predictions. The output is designed to include both the trajectory coordinates and response sentences for the questions, enabling multitask applicability. Next, going beyond predicting the possible numbers, we aim to enable our model to recognize the relationship among people. Moving away from traditional mathematical formulations, we incorporate more human-like thinking into our approach. To achieve this, we implement a multitask training strategy. In addition to trajectory prediction, our language model is trained on 5 additional auxiliary tasks. This training allows the model to understand the various social interactions, such as pedestrians' desired destination, choosing their travel directions, emulating the behavior of others, formulating groups with neighbors to work together, and identifying potential collision risks to avoid. This comprehensive approach enables the model to learn and apply social norms and reasoning, allowing better understanding and interaction with the complex social dynamics of human movements. Our language-based model has several advantages over traditional numerical methods. First, it can predict personalized working patterns by imitating a person's past behavior. Second, a language model can effectively return to the original direction after achieving an intermediate goal. Third, it demonstrates highly accurate and realistic collision avoidance capabilities. In social reasoning, our model surfaces conventional black box approaches by using directly relevant knowledge to make precise predictions. Next, following Bayesian inference principles, the language model can determine both the most likely deterministic paths and multimodal stochastic routes while ensuring the surrounding interactions. Lastly, our model provides computational cost benefits by leveraging the optimized framework compared to increasingly complex numerical models. To evaluate our model, we tested using zero-shot and supervised training approaches. In the supervised scenario, we conducted commonly used deterministic and stochastic trajectory prediction benchmarks. Interestingly, our innovative approach outperforms the traditional numerical methods across all three benchmarks. This success highlights the robustness and effectiveness of our language-based modeling in handling complex trajectory prediction tasks. Additionally, the trajectories predicted by our model accurately reflect human dynamics and show improved performance in capturing social interactions. Thank you for your interest in our work. Our codes are available online.